Talking about how we draw the structures of covalent compounds. So note that everything we're talking about this week, really, is specific to covalent compounds only and does not apply to ionic compounds. So we're going to be looking at how we figure out which atoms are connected in a covalent molecule and how they're connected and where all of the electrons are arranged. So we do that using what's known as a Lewis structure, which shows us exactly where all of the valence electrons are located in the molecule and whether or not those electrons are involved in bonds. So it shows us not only which atoms are actually directly bonded to one another within a molecule, but exactly where all of the electrons lie. One thing that it does not show us is the shape. Lewis structures are not intended to accurately convey the geometry or the shape of a molecule, and we'll get more into how we figure that out next week. So bonding electrons, or covalent bonds, are shared between two atoms. And in a Lewis structure, we typically use a solid line to represent a pair of bonding electrons. So one bond or one line equals two electrons. So one line is what we call a single bond, which contains two electrons. Two lines is what we call a double bond. Each bond is two, so if we have two bonds, that's four. And three lines is a triple bond. And that's as high as it goes. And triple bonds contain a total of 6 electrons. So each line represents 2 electrons, and that's important to remember going forward. Non-bonding electrons are also known as lone pairs, are electrons that are located only on one atom. So they're not shared, they're located only on one atom, or they're attracted to only one nucleus. So we use these, or we represent these with a pair of dots. So a pair of dots is one lone pair, which is 2 electrons. And you may see multiple lone pairs around a single atom, but they pretty much always come in pairs. Occasionally you can have a single electron by itself, but we're not really going to deal with that this semester. So to actually figure out the whole structure, we're going to be following a series of steps that will allow us to predict what a molecule looks like based on just its formula. So the first thing we need to do is determine the number of valence electrons in the molecule. And we can do that just by adding up the number of valence electrons on all of our atoms. And we can figure out how many valence electrons are in an atom by the periodic table and what group it's in. So the periodic table that I've been using in my videos has these black numbers above each of our families, which is one method of numbering the groups. Just 1 through 18 left to right, is a fairly common way to number the groups, but is not the only method and is not the most useful method. So what I've written in purple and red above those is another method that's commonly used to number the groups or the families of the periodic table that's a little bit more informative. So we're not really going to worry about the numbers associated with the transition metals down here. Those are not terribly useful. But the ones that I've highlighted with the letter A after them, for those elements, for that numbering system, the group number is equal to the number of valence electrons. So that's going to be really handy for us. Let's do this in green. So the group, let's be really clear about what I mean here. So these group numbers is equal to the number of valence electrons. So I've circled group 4A just as an example. Everything in that family, carbon, silicon, germanium, tin, lead, all have 4 valence electrons. Anything in group 7, fluorine, chlorine, bromine, iodine, all have 7 valence electrons. So just by looking at the group number, we can figure out how many valence electrons are in our structure. So for any formula we can figure out how many valence electrons are in the whole molecule just by looking at what atoms are involved. So if we do that for each of these examples, we're just going to need to find our atoms in the periodic table and add them up. So our first example, NF3, starts with nitrogen. Nitrogen is in group 5. So nitrogen has 5 valence electrons. Fluorine is over here in group 7, so it has 7 valence electrons, and that is each fluorine atom. And this subscript is telling us that we have 3 of them. So we have 3 atoms with 7 electrons each. Gives us a grand total. 3 times 7 is 21, plus 5 is 26. So NF3 has 26 valence electrons. And that means that when we draw the structure for NF3, we draw our Lewis structure, it's going to need to include exactly 26 valence electrons, no more, no less, or it's not representing the correct formula. So why don't you pause here and take a minute or two to do the next 2 examples. So try to figure out how many valence electrons are in H2O and how many valence electrons are in CHCl3. So for these 2 examples, first up we have H2O. Hydrogen is in group 1. So each hydrogen atom has 1 valence electron, and there are 2 hydrogen atoms. Oxygen is over here in group 6, so it has 6 valence electrons. So 2 times 1 is 2, plus 6 is 8. So water has 8 valence electrons. And then last but not least, we've got carbon is in group 4, so that's going to have 4 valence electrons. Hydrogen we just saw is in group 1, so that has 1 electron. And then chlorine is over here in group 7, so each chlorine atom will have 7 valence electrons, and there are 3 of them. So 7 times 3 is 21, plus 1 is 22, plus 4 is 26. So the structure for CHCl3 is going to need to have 26 valence electrons. So once we've got this number, it's something that we want to kind of keep in mind going forward, because it's our target number of electrons that our structure needs to contain in the form of lines for bonds or dots for lone pairs. We need to add up to this correct number, or we're not actually representing the correct molecule. So that's step 1, and that should always be step 1 for now. So the next step in the process is to choose what we call the central atom. So simple molecules typically have one central atom connected to multiple peripheral atoms, or they're sometimes also called terminal atoms. There are a couple different ways you can choose it. For today, we're going to look for the unique atom, meaning whichever element there's only one atom of is usually the one that's going to go on the center. One thing to be aware of is that hydrogen will never be the central atom. So if you have only one hydrogen, even if it seems like, oh, well, that's unique, it can never go in the center because it can never form more than one bond. So looking at the examples that we've got here, I think we're just going to work all the way through NF3 first, and then we'll come back and do the other ones. So we have one atom of nitrogen, 3 atoms of fluorine, so we would say that nitrogen is our unique atom, in that there's only one of it. So nitrogen is unique, means that N is going to be our central atom here, and the fluorines will be arranged around it, will be our peripheral or terminal atoms. So the next thing we want to do is to just kind of set up our skeleton, put our central atom in the center, and arrange everything else around it. How you arrange your atoms doesn't actually matter at all. so the angles don't matter. I chose to put mine in kind of a T-shape on 3 different sides, but you could evenly distribute them all the way around. It doesn't matter. And then we want to connect each of our peripheral atoms to the central atom by a single bond. So remember that each of these bonds is using up 2 electrons. So we have 2 electrons, 2 electrons, 2 electrons, for a total of 6 so far. So the next thing that we want to do is to fill up the valence shells of all of our peripheral atoms first. So we always fill up our peripheral atoms with lone pairs before we fill up the central atom. So when atoms bond, they're usually looking to fill up their valence shell because that gives them some additional stability. So we're looking to fill the S and P subshells of our peripheral atoms here. So what this means, remember that the S subshell is 1 orbital, so it can hold 2 electrons. The P subshell is 3 orbitals, so it can hold 6 electrons. So that means we're usually looking for a total of 8. This is often referred to as the Octet Rule, that you will most commonly see. Most atoms will end up with 8 electrons around them between bonding electrons and lone pairs. So right now, if we look at our peripheral atoms, this fluorine atom is involved in a bond. That means these 2 bonding electrons are available to it. So in order to get to a filled valence shell of 8, it needs 6 more electrons, or 3 lone pairs. So if we put 3 pairs of electrons on that fluorine, we have 2 electrons, plus 2 electrons, plus 2 electrons, plus 2 electrons from our 3 pairs of non-bonding electrons and our 1 bond here. So that's giving it the 8 valence electrons that it wants. It's sharing some of those with nitrogen, but it still has access to them, so they count as being part of its valence shell. And we can do the same thing for our other fluorine atoms to give them filled valence shells as well. So right now we're looking to fill up our valence shells for our peripheral atoms only. And at this point we want to check in and see how many electrons do we have. Remember that our target for this was 26 electrons. From back up here where we looked at the periodic table, we found 26 was our target number. After step 3, we had 6 electrons placed so far. 2 in each of our bonds, 2, 4, and 6. So at this point, we still have those 6 bonding electrons, but we've now added 2, 4, and 6 here, 2, 4, and 6 here, and 2, 4, and 6 here. So we've added 18 more electrons to the 6 that we had. So our structure so far has 24 electrons, which means it's still missing 2. So moving on, the last thing we want to do is to place any remaining electrons as lone pairs on our central atom. We have 2 electrons left, and the only place that we can put them is on that central atom. Our peripheral atoms are already full. They have the 8 valence electrons that they want. They cannot have any more than that. 8 is the maximum for peripheral atoms. So our last 2 electrons have to go as a lone pair on nitrogen. So this structure now has 26 electrons, which was the magic number that we're looking for. And all of our atoms have filled valence shells. Each fluorine atom has 2 electrons from its 1 bond, plus 6 additional from the 3 lone pairs. The nitrogen has 3 bonds around it, which gives it 6 electrons, and it gets the last 2 from this 1 lone pair. So each of these atoms has 8 valence electrons available to it, with varying degrees of sharing, but allowing all of them to have a filled valence shell. So let's go back and go through the same process for water. If you feel ready to try it on your own, feel free to pause here and do that before we move on. So going through the same process for water, we will want to keep in mind our total number of electrons as we go forward was 8. It doesn't really matter for step 2, so I'm going to skip over writing it there. Step 2 was choosing our central atom. So we want to look for the unique atom, which in this case is oxygen. There's only one oxygen atom to 2 hydrogens, so O is unique, which means that O is going to be our central atom. So for step 3, that means that we're going to put oxygen in the middle, arrange our hydrogens around it, and then step 4 is to fill in the valence shells of our peripheral atoms. Now hydrogen is an exception to the octet rule, sort of, because its valence shell is the first shell. The first shell only contains a 1s orbital, means it can only hold 2 electrons. There is no p subshell to fill up for hydrogen, so it can only have a maximum of 2 electrons ever. So that means that this one bond is all hydrogen needs to be happy, to have a filled valence shell. These are the 2 electrons it's looking for. Hydrogen will never form more than one bond. Hydrogen will never have lone pairs on it. So our peripheral atoms already have filled valence shells here. We actually don't need to add anything else to them. So just for consistency here, this structure has 4 electrons so far, still 4 electrons at this stage since we haven't changed anything. We're looking to get to 8, so we will need to put 4 somewhere. So step 5 is to place the rest of our electrons as lone pairs on the central atom. So our central oxygen can take our last 4 electrons. So at this point we really have no other choice. If we have electrons left that we need to place, they have to go on the central atom. There are no other options. Once your peripheral atoms have their filled shell of 8, they cannot take any more. Or in this case, filled shell of 2 for hydrogen, cannot take any more, so the rest of our electrons have to go on oxygen. And it should work out that that central atom has a filled valence shell. So we have 2 and 4 electrons from bonds, plus 2 and 4 electrons from lone pairs, for a total of 8 electrons around our oxygen, as well as 8 electrons in our structure in total. So we have the correct total number of electrons, as well as filled valence shells on all of our atoms. So now, pause here, go back and try to go through that process for our last example, for CH3Cl. So for this one, up above, we found that this was 26 electrons that we're going to need to represent in our final structure. So for this one, figuring out our central atom, we have 2 unique atoms here. Carbon and hydrogen are both unique in that there is 1 atom of carbon, there is 1 atom of hydrogen. However, because hydrogen is only able to form 1 bond, it cannot be central. So we don't need to worry about that as an option here. So knowing that, carbon is the only unique atom that is capable of functioning as a central atom. So that will be our central atom. As it happens, when carbon is present in a compound, it is always the central atom. Carbon likes to be the center of attention. So carbon is always central, hydrogen is never central. So when we go forward arranging our atoms, we're going to put carbon in the middle and connect everything else to that. So it doesn't matter what you put where. I'm going to put the hydrogen up the top, and then the chlorine left, right, and bottom. So at this point, we've drawn 4 bonds, which means we have represented 8 electrons so far out of the 26 that we need. So our next step is to fill up our peripheral atoms. Hydrogen is happy with its 1 bond. It doesn't want any lone pairs, but chlorine wants to have a filled valence shell of 8, or a complete octet. So if we give 3 lone pairs to each of our chlorine atoms, that will fill up their valence shells. Each chlorine atom has 1 bond with 2 electrons, and 3 lone pairs for a total of 6 plus 2 is 8. So each of our chlorines has a filled valence shell. And at this point, we now have all of our 26 electrons represented. We have 2, 4, 6, 8 in bonds, plus 2, 4, 6, 8, 10, 12, 14, 16, 18 in lone pairs, and 18 plus 8 is 26. So for this example, we're actually done after step 4. We don't have any additional electrons left to place, so we're done here as long as all of our valence shells are filled. We just went through and filled up all of our chlorines, so we want to just check on carbon. Our carbon atom in the center here is involved in 4 different bonds, giving it 8 valence electrons available to it, so it has a filled valence shell. So this one we're actually done and happy, stopping after step 4.